Alright, the nice thing about this is that cosine follows the same rules. It's just a little bit different, okay? Instead of cosine starting at 0, where is it going to start?
1.
At 1. And when sine gets up to 1, cosine is at
2.
Negative.
0.
0.
Oh.
Okay? When sine comes back down to 0, cosine is at negative 1. And then when sine goes down to negative 1, cosine is at 0. And then once sine gets back to 0, cosine is
1.
back to 1. Alright? So you'll see here. Wait, hang on. Sorry, messed that one up. Here, I was good until here. Put that back. Let's try this again. Alright, so we should be hitting the x-axis there. We're at the minimum here. There we go. Got back on track. Alright, so you'll notice the shape is the same as the sine curve. It's just shifted over. Alright, how far over is it shifted?
0.5.
Think in terms of our angles. Sine starts at 0, cosine doesn't hit 0 until we get to 90 degrees. Okay? So it's shifted 90 degrees, or pi over 2. Alright? And we'll see later on that's actually another property, has a name we'll look at. Okay? So all this to say, if you're working with stuff and you know the sine or the cosine or even the tangent of some angle, and you have a coterminal angle to that, the sine or cosine and tangent are all going to be the same. Alright? We know the sine of 30 is a half. So the sine of 30 plus 360, 390, is also going to be a half. And if we added another 360, we'd be at a half again. Okay? Yes?
So is amplitude only for sine, or is it also for cosine?
It's also for cosine.
So do we have to have some sort of special notation to differ the two? Would we have to say the amplitude sine is 1? Or the amplitude.
And if you were asked for both of them or something, if for some reason you had to find them and they were different, then yeah, I would distinguish between the two. But if you're asked for sine and cosine, they're both going to be 1 normally.
Okay.
Okay. Unless we had 3 times the sine of something, and then you're getting into something we're going to look at later. So I wanted to deal with that to point out those things and relate this. Kind of tie things together, what we were doing at the very beginning with angles and what we were talking about yesterday with our sine and cosine. Okay. And now I want to look at some other identities, however. Okay. So here we have our first quadrant, again, for a unit circle. And you'll notice I've picked some random point x, y. And of course, you guys know, since it's a unit circle, the radius is going to be 1. So there's our hypotenuse. I want you to think about this right triangle. In terms of theta.
I'm sorry. How can you know the
Hypotenuse?
yeah, hypotenuse 1? How can you know it?
It's a unit circle. So that's one of the things we said yesterday. A unit circle is called a unit circle because it's 1 unit for the radius. Okay? Alright, so we have this. How could I express this bottom side here in terms of theta? In a unit circle. What?
Cosine.
Cosine theta. Because that's x, we know, and cosine of theta would be x, the adjacent side, over 1. Alright? So that x length is going to be the cosine of the angle.
So the cosine is the adjacent side and the sine is the opposite?
Yeah. This opposite side here is the sine. Okay? Now, does anyone see an equation that we could write at this point?
The Pythagorean theorem.
Yeah. And what would that look like with this triangle?
Cosine theta squared plus sine theta squared is equal to 1.
Okay. 1 is going to equal sine squared theta plus cosine squared theta.
Y squared.
Because it's from the Pythagorean theorem. Okay? Now, one thing about how you're writing things, okay? Do not write this. What is squared right there?
The angle.
Theta
The
squared.
angle. Alright, that's not what this is doing. You could do that, but then you're going to be writing parentheses all day, and that's going to get really annoying really fast. Okay? It's right, but it's going to be a lot of extra writing. So, for ease, we put the square right after the sine to show that we're squaring the sine, not the angle. Okay? So we have sine squared plus cosine squared equals 1. And that is the first of our 3 Pythagorean identities. Okay? I'm showing you these, how these are derived, because they can be easy to forget. But if you remember how they're derived, it's not that hard to re-derive them. Okay? So let's derive the second one. Okay? I've got to derive the second one by dividing both sides of the equation. I got to be fair to everything. So I'm dividing everything by the sine squared of theta. So let's think about what this would equal. Sine squared over sine squared is 1. Now, cosine over sine is
Cotangent.
cotangent. So cosine squared over sine squared would be
Cotangent squared.
cotangent squared. Good. And then 1 over sine squared would equal
Cosine.
Cosine.
Cosecant.
cosecant. There we go. Cosecant squared. Alright?
Wait, why?
Well, because 1 over sine is cosecant.
Oh.
So 1 over sine squared would be cosecant squared. Okay? So, 1 plus cotangent squared is always going to equal cosecant squared. If you went back and looked at some of the problems we did yesterday and actually plugged in the values that we had gotten, it'll work out every time. Okay? That's our second Pythagorean identity. Okay? How do you think we're going to find the third one?
We divide by
Divide cosine by cosine.
Yeah, we're going to divide everything by the cosine squared. Alright? Okay? so that's going to give us sine squared over cosine squared is
Tangents.
good, tangent squared. Plus 1, of course. And then 1 over cosine squared is
C.
good, secant squared. Okay? And that's the third Pythagorean identity. Okay? So, a little bit of a challenge to just remember. Honestly, half the time I don't remember them right off the top of my head, so I just rederive it real quick in my head. Okay? If you just think about, this one's a little easier to remember. Sine squared plus cosine squared equals 1. So, if you think about it, if I divide by sine, I get 1, cotangent, and cosecant. Alright, so that's the one I get. And you can just think it through and figure out the other two pretty easily. Okay? Another way that it'll be helpful to help you remember it is in these equations, the cos are together, and the ones that are not cofunctions are together. Okay? So tangents with secant, cotangent is with cosecant. It's just another way you can remember it. Okay? Now, why do we learn this and all the other identities? Well, there are often expressions that we want to simplify that we'll need to use some of these for. In one example, this kind of shows you how we can be flexible with these. Obviously, if I wanted to, I could rearrange these, right? Algebraically. So if I wanted a sine squared, I could write it as sine squared equals, how would I rearrange it? If I want sine squared equals 1 minus the cosine squared, I would just subtract the cosine squared from both sides. Alright? If I wanted a tangent squared, I would say tangent squared equals, secant squared minus 1. Okay? So you can use algebra and rearrange them. Alright? And as we move forward, anytime you see trig functions being squared in some way and you're not sure what to do, think Pythagorean identities. Okay? Because a lot of the time that's what you're going to use. This is also helpful in solving equations like this. Let me do this, move it up a little bit. Okay? Here we have an equation 3 sine squared theta minus 5 cosine theta plus 4 equals 0. And really, without any identities, we would be stuck. There would be nothing we could do with that. However, if I use the Pythagorean identity, I can write an equation that only has cosines in it, rather than sines and cosines. Alright? And what that would allow me to do is then to go ahead and solve the equation. We'll learn how to solve those later, but I wanted to show you that's one thing that this can be used for. So, with all of that, we now have all of what are known as the fundamental trig identities. Okay? Now, don't get overwhelmed. You already have all of those. This box is in your book if you want to see it. But we have the reciprocal identities. We saw those yesterday. The quotient identities with tangent and cotangent. And then these three Pythagorean identities. So, any questions about our identities? Anything? Alright. Now, we're not going to get to all the identities today, but I do want to take a look at some things here. I want to go back to our first quadrant of our unit circle. and look at the pairs of angles that are complementary. And do you guys remember what the term complementary means? What's that? They add up to 90, okay? So, for example, the 30-degree angle and the 60-degree angle. Or the 45 and 45. Okay? Now, someone actually made this observation yesterday, I believe it was in this class. What do you notice about the 30 and the 60-degree angles?
Opposite
Yeah.
the reverse.
Very good. The coordinates are simply reversed. Okay? Now, let's think about this x coordinate for the 30-degree angle. What trig function is that again?
That wasn't chemistry, I'm sorry.
The x coordinate? That's alright.
Sine.
Cosine?
Six.
Cosine. Cosine of 30 is radical 3 over 2. What's radical 3 over 2 up here?
Sine 30.
Sine
Sine
of
60.
60. Okay? Sine of
Oh.
60. 1/2 is the
Cosine.
cosine of 60, or the
Sine 30.
sine of 30. Okay? What you're seeing here is what we call a cofunction relationship. Sine and cosine have this relationship where the sine of one angle will equal the cosine of the complement of that angle. Alright? You can see it with the sine and cosine of 45. That's why they're the same, because 45 and 45 is 90.
Why sine 30 equals 1 over 2? Like, why coordinate?
That's what we developed yesterday. Opposite over hypotenuse was the y coordinate over 1, so it's just y. So this gives us a relationship here. The cofunction identity, the first of the cofunction identities, is this, that the sine of theta equals the cosine of 90 minus theta. And by the way, depending on which book you read or which site you look at, some of them will put 90 minus theta, some will put theta minus 90. It doesn't make a difference. Okay? In radians, you'd see the pi over 2 instead of the 90 degrees. Now, this one is a little bit more obvious as far as which trig functions go together. Okay? So think with me. If sine and cosine go together, what's another pair that probably go together for the cofunction identities? Secant and cosecant, yes. And then their last one would be
Tangent and cotangent.
tangent and cotangent, alright? So, those are our other two cofunction identities. The secant of an angle will equal the cosecant of pi over 2 minus that angle. The tangent of an angle will equal the cotangent of 90 minus that angle, or pi over 2 minus that angle.
Pi over 2 and 90 degrees are the same thing, right?
Yes.
How could they be the same?
Different units of measure. It's just like, 1 kilogram is 2.2 pounds. 1 equals 2.2 because they're two different units of measure.
Right.
Yes.
Are they the same flip, like cosine of theta is equal to sine of
Yes.
90 minus theta?
Yes. And cosecant theta equals the secant of pi over 2 minus theta. And cotangent theta equals tangent of pi over 2 minus theta. And that's really why it doesn't matter whether you write it as pi over 2 minus theta or theta minus pi over 2. It won't make a difference. Alright. Any questions about our cofunction identities? These ones don't show up as much. That's why they're not one of the fundamental trig identities. We're gonna look at some other identities as well. They're they're used a little bit less, but they're still important to know. Okay. All right. We're gonna get to the negatives, and this is kind of what you saw a little bit of on the homework. We're gonna explain why that was the case on some of the homework problems. We'll get to that tomorrow. Okay? So, I've given you a little bit of practice. Okay? Here they gave you, sine and cosine. They want you to find some of these others. So think in terms of what we've looked at already. Using some of the identities. Alright, but you can practice those. Alright?